Okay, in this course, we want to talk about how to translate words to something that makes sense to computers. How can we run models on it? How can we train models on it? And as we know, for any computer software, only numbers make sense. And we can manipulate numbers and multiply numbers, add numbers. So anything that we did in neural networks have to do with numbers. So how can we assign numbers to words and sentences? So one way to do it is to assign random numbers. For example, say my apple is tasty. Then one way to deal with it is say, okay, my is 0.1, apple is 2, is 3.14, and tasty is negative 500. So that's one way to assign numbers. Yeah, you can do that. Actually, if you have a very deep neural network, you can probably train it on these random numbers, probably, because theoretically any deep neural network can understand any pattern that you're putting up there. But actually, it's not a helpful way to do it. Another way to do it is even worse than that, and that is saying that, okay, I'm looking at entire dictionary and I do one-hot encoding. For example, my would be, so imagine your dictionary has 4 words, only 4 words. My, apple, is, and tasty is that. So for my, you have 1, 0, 0, 0. Then for apple, you have, for is, you have 0. And lastly, for tasty, you have 0. That's one-hot encoding. It's possible, but in a dictionary, you may have a few 100,000 words. If you have n-grams, it can easily exceed to millions. So it's not quite efficient to do it this way, to create such large sparse vectors that we want to deal with it. So none of these are very intuitive. One of the best ways to deal with it is to do something called Word2Vec. And that's the focus of today's course. You probably have seen these examples before, but let me focus on a few of them. I'm pretty sure if you've ever heard about Word2Vec, you have probably seen this. King minus man plus woman is equal to queen. Probably you have heard that. So if we could represent words in lower dimensional vectors that would make closer words together, then probably it would be way more meaningful. For example, let's look at the distance between king and queen in this representation, and distance between woman and man in this representation. So if we train a neural network that learns about the relationship of king and man, and let's say learns a little bit of relation of queen and woman, when we train it more and more and more, and it learns more about all of these relationships, the distances that come up with in lower dimensions probably will be representative of something. So if we learn more and more about king, probably we learn more about queen as well, and the same for man and woman. So it would be very, very helpful, and it helps us to infer better. The model will be trained significantly better. Another example is, say you have a word in which you have 2 dimensions, only you have fruits and you have like tech. So these are like 2 general topics that exist in your dictionary. There are a few words like banana, like melon. There are fruits. We don't have any tech product that has these names. And there are like some tech products like these ones, like PS5, Xbox, Android. They're just techie stuff. But there's something in between. We have like Apple, we have BlackBerry, Raspberry Pi, for example. These can be fruit or tech. So if we could show these things in 2 dimensions, we probably want Apple, BlackBerry, and Raspberry only on this axis be very close. That means if I'm projecting it only on this axis, on the fruit axis, I want them to be close to the fruit categories. And when I'm projecting it on the tech one, I also want them to be close. For example, in this representation, PS5 is probably represented as, let's say, 0.1 fruit and 0.9 tech. Probably Apple is presented as 0.8 fruit and 0.9 tech, and probably banana is mainly fruit. So it's like 0.9 fruit and almost nothing tech. Let's say 0.01 tech. So this representation can be very, very handy when you're dealing with text and you want to feed it in your network. So how can we create such a thing? That's a big question. One way to do it is to use an amazing technique that is available, and that's Word2Vec. That's word embedding. And it's in its simple form. It's very simple, actually. The idea is very intuitive and simple. And that is one of those ideas that you say, oh, it makes perfect sense. It's simple. But believe me, it wasn't as intuitive before it was invented. I think the beauty of great inventions is that when you look back at the breakthrough, say, oh, okay, that makes perfect sense. But when it was developed, people didn't know about it. So kudos to the inventors of this method. So the idea of Word2Vec is simple. So imagine we only have two sentences. One is weather is awesome. The other one is I am happy. I'm going to first oversimplify what Word2Vec does in order to teach how to use it. So in a Word2Vec architecture, imagine you have a network and your inputs are weather is awesome, I am, and happy. So whenever you have weather, this node is 1, the rest are 0. Whenever you have is, weather is 0, is 1, awesome is 0, and so on and so forth. And lastly, you have weights that are connected to some hidden layers. These are some hidden layers. And these weights are actually, we're going to see later, these are the embeddings of these words. These are like some weights that we are probably going to learn. For example, weather to the first inner node, hidden layer node, it has a weight of 0.1. To the second one has 0.2. And then here you have some linear activation function that for every input that you input, it simply just add things up. It does nothing but add things up there. And then you have like some subsequent weights that gonna go through softmax, and you have some outputs. I know it was a little bit complex as I stated that, but bear with me, please. So let's say we want to train this network to do a very simple task, and that is to predict the very next word. For example, if I say, and as I said at the very beginning, this network is extremely simple, and the training set is only weather is awesome and I'm happy. So whenever I say weather, it should give me is. Whenever I say is, it should give me awesome. And when I give awesome, it probably should give me a period or end of a sentence. I didn't add end of sentence here, but you could. But since we are in Word2Vec, we are not necessarily just predicting the next word. I didn't put it there. So our task is simple. We just want to predict the very next word given a word. So here, if it's weather, we want our model predict is as the output. So I want my model to predict 0 probability that the word after weather is 0 is weather. Probability 1 that is, probability 0 is awesome, 0 I, and so on and so forth. So that's my goal. And it does it through a very simple, fully connected network up to here. And then any linear calculation is being done here, is going to go through some softmax function. We have already learned that before. And then if it makes a correct prediction, great. So the back propagation is not going to update any weight. But if it does a bad prediction, we use back propagation to update the weights so that it make a better prediction in the next training one. So let's go ahead and do it. I intentionally only put these two weights here because it would be very, very messy to do it. And for the word weather, we actually don't need more than 2 because these inputs are 0 anyways, because weather is 1, these are 0. Whatever weight I would put here or here would be multiplied by 0. And as I said, here you only add up everything, so 0 plus anything would be that thing. So the only thing that would matter for weather are these weights. So let's go to the next page to do some simple math. So this is the same thing as we had before. So here 0.1 multiplied by 1. So this node get 0.1. Everything else was 0. So if you add 0 to 0.1, you get like 0.1. And on this, on the bottom node, you only get 0.2 because everything else was again 0. So you get 0.2. I am assuming, for just the sake of this example, the weights that are going through the next layer are 0.1 through 0.6 for the top layer and negative 0.1 to negative 0.6 from the bottom layer. Okay? So now you cannot say these weights are 0 because they're no longer 0. Remember in the backpropagation one we said, oh, if we have 0, these weights are not being updated because they will be irrelevant. But here they're no longer irrelevant because this internal node or hidden layer has 0.1 and 0.2 as input. So what will be the output of this node? So that will be 0.1 times 0.1, negative 0.1 times 0.2, because these are the inputs of this. So that will be negative 0.01. For this node, for the second node here, that I put a star in, you have 0.1 times 0.2, and you have 0.2 times negative 0.2, so that becomes negative 0.02. And if you do the rest, it would be negative 0.03, negative 0.04, negative 0.05, and negative 0.06. So these are not probabilities. So in order to translate it into probabilities for each of these nodes, by the way, these nodes represent our outputs. Remember, our goal was to predict the next word that is coming after each of these words. So this node should represent probability that the next word after weather is actually weather. This node should be E, the node is ease, and so on, so forth. So as you can see, these are not probabilities, these are just negative numbers. And in the very first lecture, we mentioned that, oh, when you have these cases, you can pass them through a softmax function to assure you generate probabilities. So that's what we do now. So this was negative 0.01, negative 0.02, blah, blah, blah. And so we input it into softmax. So for node weather, the softmax, for those of you who have forgot, will be exponent of that node. You go to exponent of that node plus exponent of everything else. So let's say this is x1 was your node. The value of your node was x1. So it will be x1 plus x2 plus ex3 plus, here we only have 6 inputs, so ex6. So that will be the probability that the next node is the probability is weather is exponent of negative 0.01 divided by summation of exponent of negative 0.1, exponent of negative 0.2, and so on and so forth. So if you do it for every single node, you get 17.08% for weather, 16.9% for ease, and so on and so forth. So you may ask, Hamed, where did you get these inputs? Where did they come from? And the answer is simple. We mentioned that in any network, we do some random initialization. Imagine our random numbers miraculously give us these random inputs. So there was nothing special about these weights that I used. These were just random numbers. But as you can see, they did an awful job because they should have predicted, ideally, what we wanted them to predict was 0 here, 1 here, 0 here, 0, 0, and 0. So our objective function was like coming from cross entropies, and based on that, we used backpropagation. These weights, not these weights, sorry. So these weights will be updated, and follow that these weights will be updated. But since these, for this specific example, anything but these two weights didn't contribute to that, only these two from the very early weights would be updated. So you do it for every single one, and let's say at the very end, once you're done with training for weather, you end up with 0.01 and 1.2. So these are the values of embeddings for weather. So you are going to represent weather by 0.01 and 1.2 from here on. If after training this network, you get 2 and -1 for ease, your ease is going to get represented by a two-dimensional vector of this. What does it mean? Depends on the context, but usually it's more complicated than what we can totally understand. But what it means is projecting this into a two-dimensional word that best is able to predict the next word for this specific task that we define. But as you can guess, this is not the best way of training this method. Why? Imagine instead of I am happy, I had I am not happy as a sentence. Definitely not would have played a role here. This doesn't mean I am happy. So the context doesn't mean anything here. So we should have been more careful when doing it. So we should have probably used a better method to do it. But this is a good example to show you that, okay, so we can train all of these weights if we want, because we know a backpropagation method. There are some nuances here that I'm going to explain later when you're optimizing it. But beside that, set that aside, theoretically we can update these weights. But in real English, it's a side talk. In a real English language, we don't only have 6 words here. We have hundreds of thousands. So there are a lot of number of weights that needs to get updated. Fortunately, each round that we are coming with based on like predicting the next word, we only update 2 weights. So it's not computationally expensive here. But this is a different story right here. So we are going to discuss how to tweak few things to be able to train the model actually, because if we have these many nodes connected, we probably cannot update it. And in real life applications, your embeddings do not have only 2 dimensions dictated by these 2 hidden layers, hidden nodes in this layer. You usually have like anything between 50 to 150 embeddings there. So you will have a lot of connections that needs to get optimized here. So that was a side talk. I'm going to explain how to deal with it later. But in Word2Vec, if you're not using the next word, predicting the next word, what do we use? Which is similar but has context in it. There are 2 things that initial inventors of this method considered. One was called continuous bag of words. In a continuous bag of words, what they did, which is shown in red here, so this, and this, is what you do is you look at the words around the word and try to predict that word. For example, the input of whether is awesome for is to predict is whether and awesome. So given whether and awesome, you're trying to predict is. So this is one thing you do. So that is going to consider the context, because the before and after words are going to play a role here when the weights are being updated. The second thing we use is called skipgrams. Skipgrams is also a very powerful one. Imagine the skipgram is the opposite of continuous bag of words. So that given a word like is, you're trying to predict what is around it. Not necessarily the immediate things that are around it. It could be more than 2 things that are, if you have a big sentence, you can go more than 1 word around it. But here, given is, you're trying to predict whether and awesome. And since you have 2 words here, you want it to give 50% probability for whether and 50% for awesome. As you saw earlier, for the continuous bag of words, when we had whether is awesome, is was the only input in this case, and whether and awesome were the 2 inputs in it, and is was the only output. That's why everything else was 0. You wanted to predict probability 1 for is. But for the skipgram, it was the opposite. Is was the only input, but since it has 2 outputs in this case, we used probability as 0.5 for each one. If there were 3 outputs for it, we would use probability 0.33 for it, and so on so forth. This way, we assure that we understand the relationship of the words based on context, not out of context. And as I mentioned earlier, we are using way more nodes in the middle, like anywhere between 50 to 150 is most of the cases. And this is how you represent every single word in dictionary with a vector that has 50 or 60 values. So that's a 60 dimension representative of 300,000 dimension words, if we assume there are 300,000 like words in dictionary. So now let's go back and see, okay, yes, in theory we can optimize these weights, but we have a lot of weights to optimize on. So how do we do it? How is it possible to do it? The answer is simple. Not simple, but intuitive. First of all, as you can see, the number of inputs are limited in each stage. So we have a lot of zero inputs, and you're not updating those weights anyway. So that helps. That definitely helps. But for these weights, we don't necessarily have that luxury, unfortunately. So how do we do with it? How do we deal with it? So we have the positive cases. For example, for weather is awesome in the continuous bag of words, we saw that is was the output. So we have one output. So here we have 5 zeros. If we use 5 zeros, we have to update all the weights that leads to these zeros. So what we do in practice is we use only between 5 to 20 of the things that it shouldn't be at random. It's called negative sampling. And we pick the positive one, which is in this case is, and only update the weights that are connected to that, because everything else shouldn't get updated because we are assuming they don't even exist. And that is going to be extremely helpful. And it's just a stage of updating the weights instead of updating on 299,999 other words that are not is. We only just use subset of that, like anything between 5 to 20, so that we allow these weights to get updated, because we don't have only 2 sentences of weather is awesome and I forgot what the other one was. Oh, I'm happy. We have, depending on what you're using, we can have like entire Wikipedia. You can have entire corpus of what you have gathered from internet, the entire corpus of the books that are available copyright free. So this is a huge corpus of one. So you have a lot of training sets. So it's not feasible for each round and each word you consider all the other outputs. So this way you make sure your optimization is not going to take forever. So to sum up, what we discussed today was an amazing technique called Word2Vec. We start from a very simple example that our goal was to predict the next word, and we show that and we only have two training inputs, whether is awesome and I'm happy, but we showed that, okay, by that you can update the weights theoretically, and you can just use the weights there for your embeddings. But when we went further away, we showed that one thing we can absolutely do is be smarter and consider context. And by doing that, instead of just predicting the next word, we discussed how you can use continuous bag of words method and skipgram method to consider context in your training. And at last, I touched a little bit on what negative sampling is. That is when you have like a huge corpus and you have huge number of potential words. You don't want to update the weights that leads to every single word. You just sample a few of them, like 5 to 20 of them. I think that's the number I can remember, 5 to 20 or 5 to 25. Alongside that positive one, you only update the weights related to that. Unfortunately, for the very, very early layers, only the ones that were used and activated should be updated, because the rest are zero, so we don't worry about those. So in bag of words, only one of them is, in bag of words, only the surrounding words are inputs that are on, and in the skipgram, only one. So that makes computation here also very small, and it makes the thing manageable. And yes, so we have the entire representation of vocabulary in Word2Vec case. So we can easily use already trained Word2Vec, so we do not do things usually from scratch. But even if you want to do it from scratch, it's actually feasible. It takes a lot of time. If you have a highly specified corpus, you may decide to do it yourself, but usually not recommended. And if you want to do it, I think you have the basic theoretical grasp of it to do it. Thank you so much for being with me by the end of the lecture. I wish you luck and success.